it audible? I think audible होगा. Yes. Okay. Fine. So let me share my screen first, then we will start. Okay. So in today's session, what we are going to cover is we will talk about machine learning and deep learning, though they are separate, two separate big courses or big topics are there. So, however, for this session and for this FTP, what we are going to do is we are going to see some part of theory, part of machine learning. What is machine learning? What are the algorithms are there, and some brief idea about those algorithms. And we will focus mainly on, okay, so ये भी काम करता होगा. So this, okay, now is it clear?
Very low.
Is it low for everyone or otherwise my laptop का
I think laptop वाला ही better है.
हाँ, इसको बंद करो मेरा laptop. Okay. What about now? Is it fine? Yes. Okay. Okay. So today we are going to discuss about from the Python perspective machine learning, and we will mostly focus on how to implement those algorithms in machine learning and what are the libraries available. Oh, sorry. Okay. So, what are the libraries available in Python for writing machine learning code? And as and when it is needed, we will have a theory portion, but we will mostly focus on the implementation part of machine learning algorithms using Python. So, before moving to the implementation, so that will be the agenda today. So we are going to see ML using Python, and we'll see one or two example of deep learning. And since nowadays you must be using GPTs, different GPT models, LLM models like ChatGPT, Grok, or any other model. So we'll see how you can create your custom, how you can use those LLMs and create your own chatbot without or minimum coding in Python. How these LLMs can be used in Python and how you can import them, and what are the technologies, framework, or options are available. One of the options is Hugging Face. So we'll see example of how you can load an LLM from Hugging Face and use it in Python. Also, there is a framework called Ulama to run an LLM on your machine without even internet. So if you want to use those pre-trained model in your system and in an offline way, so how you can do it, and we'll see simple example using Python how you can import those existing models. So mostly we are going to focus on the implementation side, and we'll start machine learning and deep learning. So okay, so let me start. So before starting, how many of you are aware of machine learning algorithms and machine learning? Yes or no? So if you have a foundation of machine learning, all right. Uh, okay. So we'll have a quick introduction of machine learning and algorithms, and then type of algorithms that are there in machine learning. We'll see some of the examples, some of the basic idea of some algorithms like linear regression, KNN, decision tree, SVM, and we'll see how we can uh, implement those algorithms in Python. So when we talk about machine learning algorithm or simply machine learning, so echo is coming, two mouse at. Oh, तुम्हारा एकेडमी वाला बंद करो. आई थिंक वो चालू है. वन सेकेंड. नाउ आई थिंक दिस विल बी फाइन. यहाँ सब देखो शायद वहाँ पे दिखाई दे.
कैसे यार बैकग्राउंड चाहिए.
स्क्रीन फुल स्क्रीन तो नहीं हो गया वो आपका?
फुल स्क्रीन है सर शायद आपकी तरफ से. नहीं
नहीं,
मेरी
मेरी
तरफ
तरफ
से
से तो
नहीं
नहीं है,
है.
मेरी तरफ से तो नॉर्मल है. अ,
एक बार फिर स्टॉप शेयरिंग करो.
मैंने शेयरिंग स्टॉप कर रखी है. शेयरिंग नहीं है. नो शेयरिंग.
रमेश सर एक बार आना. ये तो म्यूट वाला ऑप्शन नहीं आ रहा. म्यूट वाला रिकॉर्डिंग वाला.
क्यों नहीं आ रहा? कभी कभार वेबएस का ही इशू हो जाता है. नीचे कुछ दिखा रहा था ना.
वहाँ पे ओके, इसको म्यूट कर दो. हाँ, आई थिंक अब ठीक होगा. Okay, I think now this might have been resolved. So, okay, great. So when we talk about machine learning, it's a subset or sub area of artificial intelligence. When we talk about artificial intelligence, it is area or study to create intelligent system, and it is quite a broad area, and there are various approaches to create intelligent systems. Most of you, those who have a computer science background, they might have studied AI as a course. They might have seen various approaches like search algorithms, heuristic search algorithms, and constraint based programming, logic based approaches to create intelligent systems and expert systems. Oh, mm, And machine learning is one of the approaches in artificial intelligence that is known as a data driven approaches, where machine learning algorithms trained over a data for particular task, and it improve over the task through the experience that machine learning algorithm sees the data. So, in layman term, when we say a normal classical programming that you do, you always know about the input, and you know about something about the procedure or the algorithm, or I would say a task, how to do it. However, you do not know about the output. So, output you do not know. So whenever if you know the task or know the procedure or the recipe, or in a formal word, if I say algorithm, then you can always uh, write a program to get the input and generate the desired output. However, in machine learning, without explicitly being programmed, means you do not know the procedure. You only know the input, what will be the input, and what will be the output, but you do not know about the function or procedure or steps that maps that x to y. So in classical programming, you know about x and procedure f in this equation. In machine learning, you do not know about this f. So you know about, you have the data that given x, this y should be there. However, there is, you do not know about the function. That is what we try to learn in machine learning, and there are various formal definitions are there. And machine learning, apart from being a subset of AI, it also borrows various concepts from other fields, and it itself has its own machine learning pipeline. So whenever you train a model, you acquire the data for particular task, and after collecting the raw data, you perform some data pre-processing, and then after you get a pre-processed data, you train your model, and the choice of the model and which model you are going to use for your problem, that again a finding or research finding question. Also, there are various approaches how to find out whether particular model will work or not. One of the layman or easiest way is to train different models and try to come up with the best fit model for your problem. And once you train your model, you test your model using test data. So you will evaluate your model, and so in the during the evaluation phase, you find out which uh, how good is your model in terms of various performance matrices. And again, there could be various performance matrices with respect to the task that you have. So for example, for some problems, the accuracy might be a good performance matrices, or in some other cases, uh, a lightweight model or the inference speed might be another choice of performance matrices. So given a two model which are working similar, however you want a lightweight model, or the model which have low inference time, or you might want to go with the model which has low training time. So there could be various evaluation criteria for which you test your model. And if there is any chance of improvement, you try to improve the model. And apart from this, if you there could be some additional steps, like once you find out a perfect model, you deploy your model in the server may be a cloud based server, or it could be a server which is on your premises and which serves as an endpoint for users. And though there is no fixed number of pipelines, though like it's here it shows 5 pipelines, you might have various additional steps also. And For example, data collection might be having multiple pipelines, and cleaning stage might be there, and number of cleaning stages might be there. Sometime you whatever the data you have collected, you are not so you want to generate more attributes out of those features that you have collected or the data you have collected. So you do some feature engineering or feature generation out of those data, and you might perform some statistical analysis to see how good is the data and whether it is going to contribute toward learning or not. And then you run the model and you deploy them into the application server, which serves to the users. So you in real world project you might have n number of steps, and it totally depends on your task and what is the end to end pipeline that you are going to build. In machine learning there is a broad classification, so those who aware of it, they know about it. So you have supervised learning, unsupervised learning, semi supervised learning, and reinforcement learning. So if we talk about data, so when I was saying you have input and you have output, so you have x and y, and you want to find out the function that maps x to y, right? However, in real world, that y, which is could be a class. For example, let's say you are trying to build a model that predicts uh, a particular review or particular news that is spread over social media is fake or real. So your output might be real or fake, or it could be based on the reviews whether it is negative, positive, or you want to predict. For example, if we collect data of 5 years of ENICT Academy, that during a course how many participants were there, and we want to predict that if we float a similar kind of course in the next year, how many participants will be there. So that could be a number of participants we want to predict, which is a number. So y could be a number, y could be a class or category, and those categories might be two categories or more than two categories. So, and depending on this, we have different problems. One problem is classification per task. So given a data you want to segregate into multiple classes, if the classes are two, then you call it a binary classification, and if uh, more than two, then you call it a multi-class classification. Also, sometimes you don't have categories to build a model, so you might be trying to predict some numbers. For example, let's say since nowadays the stock is going up and down most of the time, you want to uh, being more optimistic about building a model that can predict whether particular stock price, what will be the stock price for the next day. So what you can do, you can collect historical data from stock exchange, and then you can build a machine learning or deep learning model to predict what will be the price of stock next day. So when you are predicting a number, then this task is called regression. So you have uh, ML model, either aggregation or classification model, and that comes under the supervised learning, because the collected data you have the output y as well. So if you have x and y both you have collected, and y could be a I mean a category or numbers, then this is called supervised learning. And supervised learning again have two classification into regression and the classification. So if you are predicting category, then it is classification task. If you are predicting a number, it is a regression task. Another example, like you want to predict house prices in particular locality. So let's say you have collected historical data of 5 or 10 years of that locality, or how the price has changed, and for the given period of time, depending on the locality and the features you want to predict whether what will be the price of that house currently. So when in summary, when you are building a machine learning model to predict a number, then it is a regression task. And when you are uh, building a model to categorize into some categories, then it is a classification task. So if you have collected data which contain the classes as well, then it is a supervised task. However, if y is not available, only you have x. Any classification example that you know, real world? Any real world example of classification that day to day you are using? Uh, okay, credit card for fraud. Any other which you daily interact? You might be seeing it daily, but so you might have observed then when you whenever there is email comes to your Gmail account, it automatically goes to either primary, social, or promotion or update category. So nowadays, I hope in your Gmail account also there might be some categories on the top: uh, primary, social, promotion, updates, and spam. So whenever there is email comes, it automatically goes to either primary category or the promotion or update category or spam category. So over the period of time, Google have learned that which uh, online shopping. So for which task? So this could be a domain, online shopping. What will be the task? So in online shopping, there could be a regression task or classification task both. So categories of the products. Okay, so you hypothetically, you let's say if you have lots of inventory and then you want machine learning to categorize into different categories, then it could be a classification task. I don't know about how student data will be a classification task or regression task. So credit card fault is one, whether it is whether particular for particular person, it could be the credit card can be issued or not depending on his history of payments and the profile KYC document information. So that could be a binary classification task. Regarding voting list, I don't know how voting list would be a classification or regression task. Okay, so if you do not have if you do not have y and you only have the data, however, there is no label. Okay, so whether age is greater than 18 or not, so that but that is no, we do not need, we might not need a machine learning model to identify it. Even a simple, because you know the procedure is this at this point of time that age is should if greater than is 18, then eligible to vote or not. So you can write a simple program as well, so you do not need a machine learning. So let me give you another example. For example, you have x and y, and if I say, okay, x value is 2, y is equal to 4, x3, y is equal to 9, and x is equal to 4, y is 16, 5, 25, and so on. And if I say, uh, okay, by looking at this data, tell me about what for given x 7, what will be the y. So you can by looking at this as human intelligence, you can find out okay, so the y is nothing but x square. Image classification task and so on. Yes. So by looking at this, you can identify the function which is a square function. However, if I say, so instead of having one dimension, you have x1, x2, x3, x4, and so on. And now you have more than one input, and they have various values. And now if I say, let's say, okay, what will be the 7, because 4 was not only because of 2, there are some other attributes also. So some linear combination of this, or some linear or quadratic or any functional combination of this, there might exist any function which takes x1, x2, x3, and x4 produces y. The machine learning, you want to predict that function. It could be a linear combination of x1 plus x2, x3, and so on, divided by something or anything. So those functions you want to learn to this. However, in some task in machine learning, you the data that you collect from the real world, you do not have y, you only have x. X means x could be a single dimensional data, or you might have n dimensional data, but you do not have any y, which is a class or number to categorize data into multiple classes. So what you can do from uh, this type of data? So there could be various tasks that you can perform. For example, if you have a raw data without any category or the output, you can group similar type of data into clusters. So okay, so the out of, let's say you have 1,000 instances of data. So if I say, so okay, so some example, what the example that I'm drawing is for the structure data, where you have data in row and column form. So each row represent one data and each column represent one attribute of the data. So you can categorize those data into various clusters, or similar type of information you can cluster there. There is another any real world example of it, where you want to group data, similar data you want to group into category, into clusters, that you might have observed. Vehicle. Okay. So on airport, what will be the task? Okay. Let me show you another example. Have you gone through Google News? If you open Google News, you will find out. See, you can see here, is news about Delhi car blast is there, and which is published in the Hindu. And there is another news, same news, published in NDTV, Times of India, and other forum. What Google News have done, you can see that this block box that is shown, that contains the information from different places. However, they are similar news, similar topics, so they have clubbed together into one cluster, you can say one group. And similarly for other news, it has clustered into uh, other group, and so on. So Google is using clustering, or basically grouping of newses into some groups. And there is no category or the class or the numbers is printed. It is just collected the data, it is just collecting the data and grouping into some categories which are similar to each other. So that comes under the unsupervised learning. When you do not have y or output variable to supervise your learning task, then it is called unsupervised learning. There are some semi-supervised learning as well, where you have some data with the labels or the classes, and you have large amount of data which do not have any labels on it. And there is another reinforcement learning which work based on the trial and reward concept. So there are various tasks. Supervised learning mapped input output pair, and if you have continuous output, then it is called regression. If you have discrete set of output or classes, it is called classification. For example, predicting house prices is will be a regression task. Classifying digits. So given a handwritten digit, you have to the model has to identify whether it is a 1, 2, or 3. So you have 9 categories. So 10 categories, 0 to 9. Then this will be a classification task. Classifying email into spam and non-spam, again a binary classification task. So the whole idea is we try to learn a function that maps input to output, and the model that we train it should always perform well on the unseen data. So the type of data, again, you have for building a model, usually most of the time you have two type of data. One is training data, and second is testing data. The training data is the data that you use to train the model, and once the model is trained, you want to test your model whether how good is the model is, then you use the testing data. And there are some other categories of data also, evaluation data, which needed if you want to perform continuous evaluation during the epoch. But usually when you are building model, you use these two data set. And the whole idea is that you want to build a model that works best on the unseen data. So usually when we do not have why, we cluster data into groups, different groups. So here it shows the example of 3 clusters where each point shows a particular data. And when we talk about reinforcement learning, it is a cause and effect idea that where a reinforcement learning agent observes an input, and based on input it performs an action, which action might be identified from a set of actions the agent can perform. And how it identify it, based on some policy or mechanism, it identifies ki, okay, so this action I can take. And once the action is performed, environment agent receives an scalar award or reinforcement from the environment, and based on the reward, information about the state and the action and the reward is saved. So it is similar to the how children in the initial days learn, where they roaming around in the room or in the environment, they perform an action, and whether they get any problem out of it, then they do not perform next time. So action, like how child learns in the environment, the reinforcement learning is uh, I mean, this is naive mapping of reinforcement learning and how children learn. So in supervised learning, you have given the input and output value pair, and the idea is to learn a mapping function that maps from x to y. One of the we have talked about regression and classification. One of the basic model is linear regression model. So we'll talk about it, how it learns and how learning happens. So when we say model is learning, how model learns through the data. So linear regression is one of the linear model. So it tries to find out the linear combination of the inputs and maps to the y. So given a data, you have uh, x1, x2, some input data is there, and you have y, which is, in case of regression, it is a number, and you want to try to find out a function that maps those features to y. And this the combination of these features In linear regression model, it is assumed that it is a linear combination of models is there. So will if you have only single input and output, then it is called simple linear regression. And if you have multiple input variables, then it is known as a multiple linear regression. Like the example that we have seen previously, that given x, you have y4, 439, and 416. So you can see here there is a simple combination of the squaring of those numbers. So the function is a square function. However, if you have more than one attributes, how they linearly combine to produce the output for. This is the idea of linear regression. So we are trying to predict a function that is going to map x to y. So we start with a hypothesis. Since a linear regression model combines those attributes linearly, so we assume that our hypothesis were uh, starting from, so each attribute, let's say this x1, x2, x3, and xn are the attributes in the data. So hypothesis is nothing but the weighted sum of this attribute plus some bias. So this theta 0 is known as a bias, and this is a weighted sum where theta 1, theta 2, theta 3 are the weights that are multiplied with the input, and you get a weighted sum and you get the output y. In some literature, you might find out these are written as wx1 x1 plus w2 into x2 and so on, wn into xn. And for bias, you might having a b written. So that basically the notation you might have different, but the whole idea is you have a linear combination of the inputs and you get the output. And the whole objective of training a model is try to find out the correct value of this thetas, so that for each training data it predicts uh, exact or near to the exact value, that output that you have. So theta 1 to theta n are the model parameters, and your x1, x2, x3 are the features value, and y is the predicted value. In the vectorization, that same equation you can write as a linear combination in a vector form as well, so that represent the same thing in a shorter format. So if you have theta, so if you have theta transpose, if you multiply with x, then that gives you the same thing, where theta t is nothing but theta 0 plus theta 1 plus theta 2 plus theta 3 and so on, and your x is 1 x1 x2 x3 and x4, and when you multiply that, you get the same equation. And your theta is the model parameter vector including the bias term x0, and x is the feature vector consisting of x equal to 1. So let's create some data. So let's see an example in Python. So you might have studied about the NumPy library, and whenever you are working with machine learning libraries or any other libraries that are involved in some task, you import those libraries, and there are various ways to import it. So there are two broad ways to import the libraries. One, you write import and the module name, and you write a alias name. Alias name is a shorter form. If you want to import a library which consists of various functions or classes or variables, you want to use it in your program, then those functions can be called, or those function can be used by writing module name and the dot operator. But when you are using various functions from existing libraries, each time you do not have to write those module name, a full module name. You can use a shorter name, alias name for it. So that's why we give a alias name, like as here, for example, numpy as np. So whenever you want to call a function, then you can use instead of using NumPy, you can use NP. So here in this example, we are importing a NumPy library for array manipulation or creating an arrays, and we are importing matplotlib library to just plotting or visualizing the data. And the dot operator says that we are in the module matplotlib. We have another sub modules called pyplot, and inside the pipe, so we are using the pyplot module sub module, which is using the NumPy library. We are generating 100 data, and you will see the range we are generating up to 1, 0 to 1. And for y, we are for the one second. Okay, sorry. So okay, where were we? Okay. And just for the demonstration purpose, we have y, which is nothing but 2 plus 3 into those x that we have generated. And using the plot library, you can plot different plots. One of the plot is scattered plot, and we are uh, passing x and y to print it, and size we are giving 10. So when we plot, when you call the plot dot show function, that will give you similar this kind of output. So this is a scatter plot, and each x values range from 0 to 1, and y value is nothing but 2 plus 3 into some x, random x, so that gives you this value. And this is, suppose this is your data you have, and you want to train a linear regression model for regression task. So the whole idea is to identify a particular line or particular function or that maps correctly maps this input, so which exhibit the similar property that this input have. So how you training? So particularly linear regression model, how it trains. So in machine learning model, each model have its own training approach, training mechanism. So what we are going to see how linear regression model is trained, and then we'll jump into the implementation side, which is the important, where you will see the whole theory that we are studying. You do not have to write anything, and you can just write 3 line of code to train any model. So how the linear regression model works? So initially it assumes an initial model with random weights. So like linear combination of weights that we have assumed, w1 into x1 plus w2 into x2 plus w3 into x2 plus bias. So those weighted sum plus bias, those weights are initially assumed randomly or initialized with 0 or anything, and then iteratively we train our model so that uh, by looking at the training data, looking at the each instance, we try to minimize that error between the actual output and the predicted output. So training of a model here means to find the parameters so that model best fit the training data, and line for which error between the predicted value and observed value is minimum is called the best fit line or the regression line. And in particularly in linear regression model, we call those errors as a residuals. So for example, let's say these are the data points you have, and somehow you come up with this line that represent the data. So the residual values is just the difference between the predicted value at this point of time and the actual value. So this is the difference, this is the residual, and some of those all residuals is basically total error. Your error is there. And when we say training a model. So let's say you have started with this line and you have calculated the error. Now you want to minimize that error. So to minimize the error, you define a cost function, which is similar to the predicted for particularly regression task. The predicted value, that is giving given particular input x on the hypothesis, you get some output. So this is your predicted value, and this is your actual value, which is there in your training data. And you just calculate the difference between these two, and you have different cost functions, loss functions, like absolute mean absolute error or squared error. Here in this example it is a squared error. So you can see for all the samples, uh, I is equal to 1 to m, where m are all the samples. You just calculating the difference between the predicted and the output, and you are squaring it. So again, there is a question to explore, why we are squaring the difference between actual and predicted, that you can find out. And then we add uh, 1 by 2m term just for the computation purpose. So where hypothesis is this. So this is a question for you, why we are taking a square of residual. So how you minimize that cost function. So for example, let's say you have x and y, and so you have x1 and x2, and then 1 2, let's say you have 4, and 2 3 you have 6, and 6 3 you have 5, and so on. You have these values, and you assume, okay, so you don't know what is the linear combination of x1 and x2 which gives y, and you assume that, okay, so I'll take x1 plus x2, and with w1 and w2 as 1 1 plus bias value, let's say 1. So and then you get the output. So w1 for first instance, let's say w1 we are initialized with 1, and x1 is 1, and w2 initialized with 1, and x2 is 2, and plus 1. So you have 1 plus 2 plus 1, which gives you 4. So your predicted value is 4. The difference between predicted and actual, here it is 0. In case of this, let's say 2 plus 3. So 1 into 2 plus 1 into 3 plus 1 is 6. And again, that predicted is 6, 0. And this 6 plus 6 into 1 plus 3 into 1 plus 1. So 9 plus 1, 10. 10 predicted is 10. Actual is 5, which is difference is 5. And we add we take the square of each value and we add, so that becomes your loss of it. So you want to minimize that loss. So how you minimize it? So there is an algorithm called gradient descent. So we iteratively update the weight using gradient descent to minimize the loss. So gradient descent algorithm is there. So for that we calculate the gradient. So when we say gradient is basically a derivative or the measure of how the cost function changes with the change in its parameter. So for this we calculate the gradient of the cost function. Gradient is nothing but the partial derivative of the cost function. So if you calculate the partial derivative of this cost function, which is 1 by 2m uh, predicted minus actual square. So you might have some idea of about the partial derivative. 2 will go here and 2 to 2 cancel out, which is there. So that will be this. With respect to each parameter, so with respect to theta 1, with respect to theta 0, theta 1, and so on. So all parameters you calculate the gradient. So for all parameters, theta 0, 1, 2, 3, all the parameters you calculate the gradient, which in general form it can be represented like this. And that also in terms of vectorization can be represented by this multiplying x transpose with the vector that has the difference between x and y, predicted and actual. That gives you the vector of gradients. And how gradient descent works, you each parameter, for example, let's say if you have, in the previous example, I have only x1 and x2, and we have y. So here we have only three parameters: theta 0, which is a bias parameter, and theta 1, which multiply with x1, and theta 2, which multiply with x2. So for theta 0, theta 1, theta 2, all will be updated, and each parameter is updated nothing but by the new value of theta will be nothing but old value of theta, which was initially initialized, and alpha into gradient. So where alpha is a learning rate, how quickly or you want to change, so that this provides the magnitude to the gradient and the gradient that you have calculated. So for theta 1, the gradient was this, and you multiply with this, and you update all the weights. So in machine learning, using vectorization, all this can be calculated once. So you can, in the vectorization, you can just uh, all the gradients can be multiplied with the learning rate at once, and you can get the vectors of the weights. So there are various so before so and each iteration you try to minimize those parameters, and again you calculate the output, and you again update those weights and during the each iteration, and the objective is to minimize that loss that we have defined. So for regression task, you have different loss functions, and you for binary so classification task, you have different loss functions. So let me that iterations that you have seen here, how in Python, how you can write a code to train any model. This is, there are n number of libraries are available to support this. One of the popular library for machine learning tasks is scikit-learn library, which is uh, generally pronounces sklearn as well. So let me show you that example of it. So, so if we talk about sklearn, so this is the sklearn library. So you there are various models are there for classification and regression task, and all those models are uh, available in these libraries, and you can use those use those models. Apart from machine learning models, some sample datasets are available. So those datasets are also available in scikit-learn library, on which you can practice your machine learning models, or you can build your machine learning models on your custom dataset as well. And depending on type of task like classification, regression, or clustering, or dimensional reduction, or model selection, you have different modules in the scikit-learn library. So you have a top module library called sklearn, and inside this you have some modules for different tasks. So quickly giving you an idea about how you can implement sklearn library. So we'll see how you can load a sample dataset that is available there on the scikit-learn, and how you can divide that data into training and testing data, where we have seen training data is used to train any particular model, and once your model is trained, how you evaluate your model using test data. So in machine learning, in scikit-learn, it is easy to import. So in during the Python course, you might have seen there are two ways to import uh, any module in Python. One is you write import statement, import the module name as and the alias name. Another way is you write uh, start from, and you mention a module name, and then you write import, and then the particular module or particular function that you want to import. Because if you are writing import module, then in your code, the full module will be imported, and sometimes a module might be large enough that you do not need all those functions, you just need one or two functions for your task. So here in this example, here is, you can see from sklearn.datasets, which is a module inside sklearn library, you are importing a function called load iris, which is uh, going to be used to load the data. And since these are already available, you don't have to write from scratch. And in another module, model selections, which is another module inside sklearn library, you are importing train test split. So using those two imports, you can use train test split and load iris dataset to importing a sample dataset. So this particular example is showing for a sample dataset. So that load iris dataset function that returns data, and as we have discussed in the classification task, you have x and y, where y could be a category. Here in this particular sample data in a iris dataset, you have uh, a data set of flowers of three different categories, and all those flowers categories, you have different values for the dimension for sepal and the petal. So there are basically four attributes are there, and you have three classes of flowers are there. So the sample data sets are moduled such a way that from each sample data set, if you uh, use dot data, then you get your x, and the target output you get it using uh, writing dot target. So from iris dataset data we have loaded into x, and target we have loaded into y. And now for machine learning model, you need training and testing data. So you have a 10 train test function to divide that data into training and testing data, and that takes your x and y and the test size. So how what is the portion that you want to assign for training, and what is the portion for assigning testing. For example, here you have set 0.2, which means you are assigning 80% of data for the training part and 20% data for the testing part. So that is about loading the model, so loading the data. And once the data is loaded, uh, you can fit any machine learning model. For example, let's say there is a model called logistic regression that okay so that is there in the different categories of sklearn. So in the linear model, you have a logistic regression model, you can import it, and once you import it, that imports a class of that model. So another small observation, if you have in the import statement, if anything that is written starting from capital letter, you assume that this is a class, and you are importing that class, and that class have the implementation of the theory that we saw and we are going to discuss in logistic regression as well. Though we have just covered the linear regression, this is just an example of it. Using the class and using the constructor, you create an instance of that model. So you can see here there is a only three-step task. You instantiate a model, provide some hyperparameters, you using that object or a reference variable, you call the fit function, which performs the same task iteration by iteration by training a model that you read about the theories of each model, like linear regression, decision tree, svm, that performs the training part on the training data. And once it is trained, you can uh, predict, again simply calling a predict function on the testing data. And once you get the predictions, you can calculate the accuracy score between the prediction and the actual data that you have in testing. So basically, using scikit-learn, it is only of three line of code. One is instantiating a model, then fitting a model, and then evaluating a model. That's it. So what we are going to do is we are going to take a break. Though this is a simple example of three steps, we are in after a session that ma'am will take, Dr. Neeta Nayan ma'am will take for neural network. And after that, we will continue with this session where we are going to see how hyperparameters can be tuned and how the hyperparameters can be searched. And yes, I'll share everything. I'll share these example slides as well. So we will build on this preliminary code that we have seen, loading the data and fitting a model, and then we are going to see how further experiment and analysis we can do with this. Okay, so I'm taking a break here. Meanwhile, ma'am will continue with the neural network part. So we have, just in summary, we have studied about linear regression, and we have seen a simple demonstration of how you can use sklearn library for this.
वो सिर्फ academics का और यहाँ से वो रिक्वेस्ट चेंज किया मैंने से होगा ना
रिक्वेस्ट कोई रिक्वेस्ट आया ना रिक्वेस्ट जानने पैनलिस्ट में तो that is okay.
Mute was.
Unmute.
Now, yeah. Yeah.
But you have to click on share screen.
So, but where do I? Here?
Yes.
Where is the share screen option? Oh, share.
Share screen के लिए
Share screen. Yeah, it will be start broadcast. And then it will. Yeah. No. Now it will show this.
Yes. Okay. Now your video is off. You can put video muted or so unmute. Again.
Yeah, no, we can. Okay, let's keep this fine. I'm audible there. You have muted me. Yeah, it is shown there. That video is muted, but this is. Can you hear me?
Can ask the participants.
speak something.
Yeah. Can you hear me, participants? Hello.
Just a minute, ma'am. We have to
Okay.
send one message to Zoom.
Okay. So I should explain feed forward approximately explain करना चाहिए basically. Off? Yeah, that is visible. So I should make off stop video. Okay. No. Now so I'm audible. So let's start with understanding neural networks. So here is a slide which is showing you the brief history of when neurons were conceived. So in the very early 1940s, McCullough and Pitt started thinking that can we make the machine behave as intelligent persons like the humans. So they thought that we will mimic the human brain cell, which is called artificial neuron. Now, how the artificial neuron something like this. So on the left, you have a human brain cell, which has a nucleus at the center. It receives signals from the various muscles or organs attached to it. A summation of these signals, and if they are strong enough, it passes a response to the body if something is to be done. So this kind of structure was mimicked artificially, that we have a cell body like the human brain nucleus. This cell body should have ways to receive input. So the input is coming in machine learning, the input is denoted as X. And this is multidimensional, so we call it as raised to power, let's say it is d by 1. So the data we are representing is a d-dimensional vector if it is a simple input. This is X. This is d by 1. So like in linear algebra, input is a single sample is represented as a, and if we have n number of such samples, this vector forms one sample as a row, that let me call it x1, then x2, and like this we will have xn. So x transposed is becomes a vector. So data matrix is now n by d, because we have n samples and every sample is d-dimensional. So here you see that this d-dimensional data is going as input. You can see there. It is every input is connected to the cell with the weight, corresponding weight to it. And this weight is called parameter. So we do what we are doing, which is, and we are doing W1 naught X naught plus W1 X1. This we do till WD XD becomes summation of WI XI. This is what we are calling here this summation. And B is shown separately here, which is called bias term. This W naught is that bias term. Corresponding to the bias term, because we want to add it as it is, this X naught is kept as 1. So this X naught will be 1 everywhere, so that the summation will come as this W naught plus W1 X1 plus WD XT. So we write it as, because this is kind of a dot product, so we write it as W transpose X. This becomes the input, which I am writing as WI XI. I is varying from 1 to D because it is D dimensional. अगर separately B करना है तो 1 to D and then I do a B, and otherwise I do 0 to D, and this becomes W transpose X. Is this all right? Somebody please respond that you understand how input, like Satinder sir was saying, input is passed as a vector. Yes, very good. So now we apply, as I said, in the human brain, we see that if the input is sufficient enough, for example, you are touching a hot stove, and if the temperature is very high, we send the signal that withdraw your finger, withdraw your hand. So we need to activation function, which is called machine learning term, over to this summation, and depending on the activation is greater than, in this case the bias is the threshold, so we say WI XI, this summation, if it is greater than some threshold, so I can say summation WI XI minus threshold is greater than threshold minus threshold, so I say WI XI minus threshold is greater than 0. Then it is, let's say it is a binary classification, it is 1, that is withdraw the hand, else it is do not withdraw the hand. So this function is called your activation function, which simply here is the threshold activation function. And now the bias term will be, this threshold will be minus B. Is this all right for this simple case to understand this? So now you see here, this is what it is shown as. Every X has a corresponding weight vector associated with it. We do a summation, we add a bias to it, and then we apply activation function over the summation, and we get a output which is called Y. In machine learning, the output is denoted as Y. Since our X was, the whole data was represented as a matrix X, which was n by D. This is n and this is D. So the input is n by D. And the Y is simply a class. How many Y's are there? As the number of n's. So this is Y is a simple vector which is n by 1. Corresponding to first symbol, what is Y जो हमें चाहिए है, desired class क्या है, ये भी हम input देते हैं. So this is 1 for class 1 and 0 for class 0. This is a supervised learning model where you, for corresponding to every input, you are specifying a desired output. Machine learning में आपने देखा है जो traditional programming करते हैं अपन, उसमें क्या करते हैं, we have a program here. You give a input, and depending on whatever the program is, you get a output. This is traditional programming. Okay. In machine learning, it is slightly different. For the applications which cannot be coded analytically, which do not have any formula, for perceptive applications, for example, you want to distinguish Caucasian faces from Indian faces. So we cannot describe an Indian face in a particular formula. It will vary from person to person, but it is very easy for the humans to understand. So for such tasks which are very easy for the human to understand, but they are very difficult to encode, we need machine learning. We learn by example. And what are these examples? These examples are the data. As the human learns with experience and become expert, we want to feed the same experience in the form of data or example to the machine, so that they learn what is distinguishing a Caucasian face from a Indian face. For example, you want to distinguish various vehicles. So to a child, you show various vehicles. This is a car, this is a truck, this is a scooter, this is a bicycle. So the car, scooter, truck, bicycle, with every sample, you are telling the label. Similarly, in machine learning, with every sample, you are telling the label, and the machine will draw a program out of it, hypothesis out of it, and then you will get the program which you will later on use on data which is not labeled, and you'll classify whether it is a truck or it is a bicycle or it is a car. So in machine learning, we give both X and Y as input, and this computer gives us a learn program. This is called the training. Now I have this learn program. I give input to it, input image, and I get a corresponding output, the expected output, which should be as good as how well I have learned my machine has learned the program, which will depend on how much large was my data and how strong was my hypothesis. So जितना data ज़्यादा से training करेंगे, उतना अच्छा अपना training program होएगा. So here in machine learning, you see here, I pass on input X and I have W and I get a Y. So X and Y are defined by the problem. And what I want function which is acting on and it is giving me a Y. So I want this function. So what I am learning, I have to learn X and Y, as I said, is defined by the program. I have to learn this W vector which satisfies X. It gives me the corresponding Y for all the input train data, then the machine has learned. So that was a simple neuron. Now solving linearly separable problems. What are linearly separable problems? They are something like this. If you have two classes which can be separated by a line, then it is called a linearly separable. I can find any line. This is also satisfying. This is also satisfying. This is also satisfying. So for example, and or problems are called linearly separable problems. But what happens when the problem nearly separable? For example, here one class is enclosing another class, not separate it. So what we need is we need a non-linear neurons came into being which are capable of solving non-linear problems, and we need a special activation function which is also non-linear. So there was a dip in machine learning 40s. We propose that we have defined an artificial neuron which is capable of solving everything, which was called a perceptron, and it was following the gradient descent algorithm, and it is capable of solving everything. But in the late 60s, it was identified that this linear problems, what will happen if the linear problem is like this, what will happen if it is a non-linear problem. For example, here we need at least two lines to separate it. So it was identified in the late early 70s that use multi-layer perceptrons. Then there are multiple layers of these neurons interconnected to each other. Then they are capable of solving non-linear problems also. So a non-linear activation function. So what is a non-linear activation function? So here I am simply showing you what is an activation function. It is doing every input. Now when we have multi-layer perceptrons, this is input layer, which is called, this is the output layer, and there are hidden layers in between. The number of nodes in the hidden layer can be as the number of nodes in the input layer, or it can be less. You can define number of nodes for every layer. And then you have output layer, which is dependent on how many number of classes. Now, this input is multiplied with this weight. This input is multiplied with this weight. This input is it is fully, and there is a summation here and the activation function here, which becomes input for the next layer. So now notation changes. Every node is denoted as an activation function. If it is the input layer, superscript is denoting the layer, so it becomes 0, like here, 0. First node, second 0th layer. Why screen share has stopped? We have to again start it. Share screen, broadcast. I hope it is coming. Hello, तो आना चाहिए. Okay. Yeah, it is coming. The connection got broke. आ गया. So now you denoted as A1 through N. The layer number is denoted as a superscript, which is 0. Then you have a second layer, which is denoted with the superscript as 1. The nodes are denoted A1 through AM. Now, because now it becomes a two-dimensional kind of weight and nodes connected between layers. So this is the weight which is connecting the first node to the first node here. This is the weight which is connecting this second to the first, weight which is going from this third to the first, fourth to the first, like this. It is all fully connected. So this weight matrix, weight vector becomes a matrix which is connecting n nodes to m outputs, and this is shown here. All the node to the nodes to the second input is shown here. Similarly, it is here, and it is every weight corresponding input added to bias and then the activating on it. So this is shown here. Activation function symbol shown here is for sigmoid weight. This highlighted activation shown here denotes sigmoid of the weight 0 A 0th layer activation vector plus B 0th layer bias as shown here. I hope डायग्राम देख के आपको समझ आ रहा है. कुछ नहीं समझ आया तो यहाँ पूछ लीजिए. सिस्टम की तो है, आवाज आ रही है कि नहीं आ रही? दिख रहा है ना अभी तो? प्लीज रीशेयर द स्क्रीन मैडम. Somebody type, is it visible? Hello? Yes, good. So now we came up with different activation functions. The previous was this activation function, which is called a step activation function, which is a threshold function. Let me draw it here. जो अपन ने अभी तक किया था वो क्या था? If it is greater than threshold, this is a threshold value. This is x summation w transpose x, and if it is greater than this threshold, I give a output which is 1 for these values. If it is less than the threshold, I give a output which is 0. So this is a non-differentiable. It is very difficult to find out the exact threshold value. And when we are doing classification, slight change in the input, if it is slightly less than this threshold by, let's say, 0.01, we are committing a mistake, zero class. So it is not good. We need differentiable functions which are very suitable for gradient descent algorithms, and we need non-linear activation function. The first non-linear activation function is a sigmoid activation function as shown on your screen, which I am drawing, outlining with red. So whatever input x, this x is neural networks में करेंगे. So sigmoid activation function is shown here in the form of what it denotes analytically. It denotes its functional form is 1 over 1 plus e raised to power minus x. So it tells me the degree of confidence I have in my prediction. So if it is a class 1, 0, I should predict output which is close to 0. And if I am not sure, 50-50% output, this sigmoid function is ideal for this, because if I feed a large input positive value, that summation is very large and positive, W transpose X is very large and positive, I am very sure that it is class 1. So then let's say that large positive value is e raised to power minus infinity. So God, again, what's wrong with the connection? It's coming up. The connection is getting broken. I am so sorry. Oh my God. So इसमें है ना? No, इसका तो ये चलेगा. I've taken hotspot, but still it is poor connectivity. I should join the institute, that thing. Okay, so if it breaks again, I'll. Here, let me conceptually show it to you that if it is a large positive value, I can say it is a large positive value, which is, let's say, plus infinity. So e raised to power minus infinity. Now e raised to power minus infinity is what? It is 0. So it becomes 1 plus 0, which is equal to 1. So for large positive values, this sigmoid saturates to 1. And for large negative values, it will give me 0, as you can see, minus and minus infinity. So this becomes 1 over 1 plus e raised to power infinity, which is 1 divided by infinity is equal to 0. So for large negative value, it converges to 0. And for a 0 value, what it will give me is e raised to power 0, which is equal to 1. So it is 1 plus 1, which is half. That is I am 50% sure. So my threshold automatic becomes this. If the input is 0, my output is 0.5. That is, I am 50% sure. But if my probability, so now I am mapping my class with the probability. So if the probability is below 0.5, I am not sure it is a positive class. So I output a 0. If the probability is above 0.5, I am pretty sure that my class is 1 and I output 1. So the sigmoid gives you for a value which is less than 0, my class output will be here. It is 0, and above this the output will be 1. So it does a binary classification. Now the problem with this sigmoid, it is non-linear. Of course, you can see it is differentiable and continuous. You can see here. The problem is when we take the gradient. Gradient is the first derivative of a vector is called a gradient. For multi-valued multi-dimensional values, the gradient, the derivative becomes a multi-dimensional vector. That's why we call it a gradient. So when the value is saturating to 1, if I take a derivative here, the derivative will be equal to 0. And when the values are saturating here at 0, the gradient is again 0. So this is the problem of vanishing gradients. All right. The same thing happens with tan h. Tan h is the function which is shown here. You can see it here. Now I am outlining with blue. It is represented as e raised to power x minus e raised to power minus x divided by e raised to power x plus e raised to power minus x. Now this, when we are interested having the classes as 1 and minus 1, then tan h is the preferable function. Tan h is convertible sigmoid, and sigmoid can be converted to tan h. Only difference is that in sigmoid, the classes are 0 and 1. In tan h, they are minus 1 and 1. Both face the same problem. When it saturates to plus 1, the derivative at this area with a small change in x, the change in y is 0. Similarly, with the small change in x, the change in y is 0. So this is a vanishing gradient problem. So to overcome this vanishing gradient problem, in the late 80s, early 90s, we came up with the ReLU activation function, which is shown here. ReLU activation function is, it is you output the maximum of 0 or x. That is, if the input is positive, we give the output as same. If the input is negative, we club it to 0. So here it is continuous function. The derivative will be always 1. So you don't have the vanishing gradient problem, but it is cutting off the negative values, which is 0. So derivative below, for the negative values, it will be 0. And for the rest of the values, it will be 1. And if we have multiple classes at output, the preferred activation function is this softmax function. You know that e raised to power x value will be varying from some minus infinity to some plus infinity, from 0 to 1, depending on minus infinity to infinity. So we want to, if there are multiple outputs, supposing this is probability 0.7, it is saying it is 0.6, 0.5, 0.4. We need the final class as the class with the highest probability, and the sum of these probabilities should be equal to 1. So what we do is every output divided by the summation of these output now becomes between 0 and 1. So whichever class output is highest, we take it as the output class. This is preferred for multi-class classification, which is called a softmax function. Now, I'll quickly show you what the neural networks, how they learn conceptually, and then we will demonstrate how to construct a neuron, and let's see how the various weight initialization acts onto it. So here is an example onto your screen, which shows a 4 by 4, 2 by 2 image as input. So input is 2 by 2. Now I need I am constructing a new neural network connection, multi-layer perceptron kind of thing. So the input I'll first convert this first row as the vector, this. And this second row is appended as a vector to the first. So this input, which was 2 by 2, it becomes a 4 by 1 input. All right. The first input goes here, second goes here, third goes here, and similarly fourth goes. So every neuron in the first layer, this is the first layer. How many pixels the first layer neuron is getting affected with? Anybody? This is the input layer. As shown here, this is the input layer. Number of neurons in the input layer are 4. Every neuron is getting input from a corresponding pixel. So its receptive field is 1 pixel only. फॉर एग्जाम्पल आपको बहुत बड़ी 25 by 25 इमेज है, सो 25 into 25 is something that is the size of the input, but every neuron is seeing only 1 pixel. This is called receptive field of the neuron. So this will be getting activated depending on what is the input of this particular neuron. If it is near to 1, then of course it will activate, and if it is near to 0, it won't activate. So I'm showing here, this blue line is showing you the receptive field of this neuron. Similarly, the next. Now you see the second layer neurons. The second layer neurons I am marking with the red pencil. These are the second layer neurons. Now these second layer neurons are getting input from this layer as well as this layer. So they are getting input from two neurons, which are getting affected by the values of these 2 pixels. So the receptive field increases from 1 pixel to 2 pixel in the second layer. Similarly, in the third layer, which is here, the receptive field is this and this, which is these 2 pixels and these 2 pixels, that is the full image. So the receptive field increases. So what I want to emphasize is the input first layer is learning the low level features, pixel level, points हैं या नहीं है. Next layer is joining these points and maybe learning lines. The next layer is joining these lines and are learning the corners. The next layer will be joining the various corners and arrive at the shape. So the first neuron layer is learning the low level features. The last neuron is learning the various classes, which are called the high level features. And finally, you get a classification. So in neural networks, we feed the input to the previous layer. The activation function are computed at each layer, and this output will be fed as input to the next layer, to the next layer, to the next layer, to the last layer. It will give a output which is visible to us. We'll check whether the output is the desired output, compute the error, and because the error is computed at the end, we want to see how each new neuron was affecting this error. What small change in a parameter at a neuron is bringing a change in the error. So we differentiate that all with respect to the parameters till the first layer. We first back propagate the errors, then we feed forward, we compute the output, compute the error, back propagate the error, then update the weights. Keep on doing this, which is called feed forward back propagation algorithm, and we learn the final weights which satisfies every input and gives us a output. This is called feed forward back propagation algorithm. Quickly, I am showing you, here is an example. You can see for digit recognition 1, 0, 9, and 8. So 1 is decomposed as this small line segment, this small. This will combine and give us a 1. 0 is divided into various line segments. 9 is divided as a loop and line, and loop is further divided into various line segments. So the earlier layers are learning the various line segments. The later layers are combining these and finally learning the digit, as you can see here. So what neurons which were active in the input is triggering some neurons here, some neurons here, and you get a output. Okay, I'm not going into the details. If you want details of feed forward back propagation, we can have another class, but I can just show you uh, feed forward back propagation, which is where is feed forward back propagation? Dakshita, you will see it somewhere. Where is that? There was a note which was feed forward. Yeah, feed forward. So you see here, please look on the screen. We have the input. Input is getting multiplied by the corresponding weights. We fed it here. Output of this node is produced like this. Activation function over this weight into this input plus this weight into this input. We get y1. Similarly, we'll get y2, this weight into this input, this weight into this input, fed here, activation function f2, you get a y2. Similarly, you will compute a y3, this weight into this input, this weight into this input, summation, activation function y3. Once we have y1, y2, y3, we'll multiply by their corresponding weight, fed here, and we'll get a f4, which is weight from this 1 to 4 into y1 plus weight from this 2 to 4 into y2 plus weight from 3 to 4 into y2. This is the summation, activation function f4, and it gives you y4. Similarly, we'll get a y5 here. Is this all right? And once we have y4 and y5, we'll compute this and we get a final output y. So once we have a final output y, now I have to compute the error. So this was a feed forward part. I compute the error. I am given a y. What is the expected y? So I'll do, let's say my y is y tilde and this is the expected y. So I do a square of this because error is dimensionless. It can be positive and negative. So we do the summation of this error and we find if the error is positive, here we are somewhere here, we'll differentiate it. We have minimum error for this function is somewhere here because it is a square function, so error function has a shape like this. So if we are somewhere here, the gradient here is positive. To arrive at the minimum error, I have to decrease this parameter by some value so that I arrive here. If the error was negative, I am on to this side, error is negative, then I have to add something here so that I arrive at the minimum value. So this, ये जो error आया है, ये error हर node ने कितना contribute किया है इस error में, corresponding to its weight, the error is contributed. So you see here back propagation. What is back propagation doing here? I computed the error. Now this error is back propagated how you see here in the first here. So a small change in this weight, how much it will affect this input into this weight will give some output which will be affecting this error. So इस error का इस node से क्या है, कितना error पे affect कर रहा है, delta 4 is in proportion to the weight which is joining this and this. जब analytically gradient निकालते हैं तो it comes the factor of this weight. That's why I am showing you here. And similarly, error which is propagated by to this is W56 into this error. So once we have errors for this layer, The error in this layer will be यहाँ पे जो del 4 into W14 plus this del 5 into W15. So this is the del 1. Similarly, you will compute del 2. Similarly, you will compute del 3. And then we will update the weights. Update happens that for the I plus 1th iteration, the previous weight, this is gradient descent. आपको अभी उन्होंने सर ने बताया था ये आपका जो फंक्शन है दिस इज डिफरेंशिएटेड विद रिस्पेक्ट टू द वेट कॉरेस्पॉन्डिंग वेट दिस इनटू दिस व्हाटएवर इज द डेल एंड इनटू सम इनपुट आएगा ये आता है तो दिस इज वी आर प्रोसीडिंग इन द नेगेटिव डायरेक्शन ऑफ द ग्रेडियंट जो ग्रेडियंट डिसेंट है इसलिए माइनस साइन सो प्रीवियस वेट minus the learning rate which is a small value into gradient. We update the weight and then we feed forward, compute the output, compute the error, back propagate the error to the previous layer, feed forward, learn the weights till the error reduces to the training error is plotted like this. This is the iteration. This is training error. With every iteration in gradient descent, the error should decrease. So when it is sufficiently small, large number of iterations, we say the network has learned. So this is feed forward back propagation. Now we'll show you a demonstration of a simple network. Dakshita, can we join? You help, excuse me, you help Dakshita to join her system, already joined. So you present and let me stop here so that we can show them the let me break it. You are joined? Yeah. Yeah. This show her screen. Okay. Screen.
Is my screen visible?
No, it will show here. The screen is not visible.
It will take a minute or two.
Yeah, it is visible. Can you make it like increase the size of the display? Yes. Now you show. Okay. Yes, here.
Okay, so this is a small demonstration of multi-layer perceptron. In this, firstly, we have imported some necessary libraries, NumPy, of course, for math, and sklearn for importing dataset. Here we are using Iris dataset. It contains 4 classes, but for this code, we are for this to make it binary classifier. So this is the dataset representation. This is the dataset feature. Sepal length. There are 4 features and 2 classes, and also we have labels with this dataset. So
you show the input. Run it so that they can show what is they can see what is x, which is the input.
Here is the output now. I'm this
onto the screen.
Yeah, this is the output.
Yeah. So you and the y is the label.
The label and x is these lengths.
Okay.
So first of all, we always normalize data so as to get good convergence results. So this is the visual representation of 100 samples we have taken. Screen lag kar rahi hai.
Hang over. No, let's wait. So you can see there are 2 features, sepal width and sepal length. and we have hundreds of data. When you plot it onto the feature space, these are visible like this. So they are from two classes. There is a zero class represented as purple, and there is a one class which is represented as yellow. So now,
Now we have data into training set and validation set. We divided 80% of the data set into training and 20% into test set. Now we are defining our neural network. For this contain input layer, hidden neurons, and one output layer. So
slowly, because there is a lag. So at the screen. Now the network defined is like this. X has 4 inputs. So you see 4 nodes onto the screen. Again, there is a lag. Yeah, you see that. And in the hidden layers, we can have as many number of nodes. This is our way. So we are increase more nodes in the hidden layer. Every input node is connected to the hidden layer with the corresponding weight. And then the hidden layer nodes are connected to the output layer through another weight matrix. So it's shown here.
So this is how we define a structure through code. In this, we have taken 4 input node and layer and output node. So makes some function for our activation function. We have defined 4 activation function: linear, ReLU, sigmoid, and 10H. We can check and use these one by one so as to see the difference in the output. And we have defined the function for 2 losses: mean square error and binary cross.
We'll show only mean square error. There is a lag in the screen. Just show the first activate. So we have defined in the code we'll be sharing with you. We have defined various activation functions, which I have just described to you. The activation functions are linear activation function, which was the simple step function, then ReLU activation function, then there is this sigmoid activation function, and then an activation function. But the screen is, you can go here. There is a definite time lag. So is it connected? It is not. Share again. Share. Yeah. Now it should be visible.
Is it?
Oh, now it will show.
LAN भी connect कर ले.
Yeah. Share.
Okay.
So the activation functions are defined here onto your screen.
Yes, we have defined ReLU, sigmoid, and 10H activation function and 2 type of losses. Here, you can uncomment when we give you code. You can uncomment and see what changes are there while we are changing the activation function. So here we are continuing with sigmoid activation function and mean square error loss. So this is the structure of network we have defined. It contains input layer, hidden layer, and output layer. So you can uncomment anyone, and this is the parameter, and you can see how the output changes when we differentiate the parameters. So these are when we run this cell, these are the initial weights we are dealing with, and this is the bias, and these are another weights we have shown in figure. So
the weights of the first layer and the weights of the second layer. So we have initialized them as to some random values.
Some random values.
Some
yes.
random values, and preferably we were planning to show you a demo what happens when they are initialized to 0, what happens when they are initialized to large positive value. If there will be another class, we'll show that, but presently we are simply showing you the working of the network. So preferably you have to initialize the weights from a normal distribution with the small variance, so that the weights do not vary from each other much.
So here is the code. Firstly, we will perform a forward pass, then we'll calculate the error. We have defined above the error function, loss function also. Then we do a backward pass and see in each iteration how it is going to differentiate. So for first iteration, this is the result for all the 100 epochs. We have 100 samples, so there is a long, huge data. So first of all, our x value is this for all the samples. Then we have these are the labels. Then after first epoch,
One epoch is you pass on all the input data. So all the 100 data will go input in one epoch. The matrix is 100 by 4 was the dimension.
Yes.
So it was 100 by 4. And it will be multiplied with the weight matrix, which will be 4 by how many nodes are in the hidden layer, which is I think 5. So
Yes.
4 by 5 layer, and you will get 100 outputs and the 5 outputs, and these 5 outputs are further connected to the final layer. So you will have a weight matrix of 5 by 1 there, and you will get the final output y. How many outputs will be coming in a epoch? There are 100 inputs, you will be getting 100 outputs, and you have 100 given outputs corresponding to the input. So you will compute the vector difference, you will square it. When you square a vector, it becomes vector transpose into vector, that is a dot product. So you do the subtraction of the two vectors, you square them, you compute the error, back propagate the error.
So this is the whole process in first epoch. Firstly forward pass, then error calculation, then backward pass. After that, the training loss and validation loss are 2.7 and 4.1. After some iteration, we can see that the loss are getting decreased. Wait a minute. So the after 10th iteration, the loss is reduced to 0.2 and validation has reduced to 0.22.
Have we plotted the training?
Yes,
Okay.
yes, we have
Can
plotted.
you show them?
So
Because
after some time, you will see that it will the loss is not decreasing, and now they are becoming constant. So here is the graph we have plotted.
this is the
Firstly, the loss is reduced to some extent. Then after that, there is no change. The loss are continuous, and we have got the decreased loss result.
So we iterate it for large number of iterations, so that we see that if there is no change in the weight updates, and that means there is no, the weights are no more learning something, because there is no change in the weight update in the gradient descent, and the loss itself, the magnitude of the loss is below a threshold, then we stop training. And you see the training loss is plotted with the help of the blue graph, and the validation loss is once trained, then you check it on to the 20% data which was not used in the training, and when we check that error, that is also coming closer to the training error. Is that all right? Changes करके दिखा दो एक, just flick the data, you
Okay.
permute the data and you run it again.
Let's change our activation function from sigmoid to reloop.
So you practice that with different activation functions, and then you uncomment the activation function that you want, and then you run it.
So this is the result we are getting. There is huge validation loss, and training loss is almost constant.
ReLU learns very fast. So preferably, because due to the vanishing gradient problems, there was another dip in the neural network research, which was, as I said, in the 69 or early 70s, when it was said that the vanishing gradient problem was identified. But then ReLU activation function was launched in early 80s, which overcome the vanishing gradient problem. So in the hidden layers, the preferable activation function to be used is ReLU, while at the output where we are doing classification, the preferred activation function is for binary classification, it is sigmoid, and for multi-class classification, it is softmax function.
So you can change the layers or neurons in the layer, or we can change the activation function, and we can change the learning rate as well. If the learning rate is very high, the output will be unstable. If learning rate is very low, the model will learn very slowly. We can change the hyperparameters like epochs and all, and we can see the changes, how the graph is changing, how the loss is decreasing, and how the weights are updated while we are training the model.
You can increase the number of layers, you can change the number of nodes in the layers, you experiment with different learning rates. If the learning rate is very high, then you will be going from positive loss to negative loss, so you will be flicking around the minimum, you won't be converging. So the learning rate should be very small initially. It can be large when we are away from the solution, but as the iterations are increasing, the learning rate should keep on decreasing so that you do not overstep the minimum.
Now next experiment or estimate.
No, but we can only show this much only.
Okay.
So I hope you have understood something about neural networks, feed forward and back propagation. We'll share you this notebook so that you can practice yourself also. And I'll share the slides also jitna usme kiya hai. I hope you will understand something. Is that all right? Any questions? Ma'am, please share this notebook. Yes, we will share. Okay. So I hope you understood. So we will break for 10 minutes and then Satyendra sir will continue. Okay. तो अगर वो कल बोलेंगे तो कल